I woke up at 4 a.m. and immediately went to my phone to check the results.
I saw the emails and my first reaction was, we've done it.
And I started jumping up and down at the airport. I started crying and I was just like, I can't believe it.
I felt like I was seeing one of those moments that's really a once in a lifetime kind of moment in science.
It really is a Wright brothers moment. It was a man landing on the moon.
Hang on, what happened? We gotta go back to the beginning.
So NIF is the world's most energetic laser. It has 192 laser beams. And we use those laser beams in this large 3 football field size facility to compress little peppercorn sized capsules of hydrogen fuel.
And that capsule is filled with deuterium and tritium. And as we put all of this energy from the laser into the capsule, we compress it really quickly and it gets really, really hot and really, really dense really, really fast. As those atoms get really close together and really hot, they fuse and they release a lot of energy. It's just like what the sun does.
And the purpose of fusion is we want to continue to keep doing that, continuing to fuse atoms and generate more and more energy. We have done that for many years on NIF. And what happened back in December, we actually got more energy out from the experiment than the energy used to actually start the experiment.
And a lot of people are like, how can you do that? You're violating, the fundamental equations of physics. And you're not actually, because what we're doing is that energy and mass are interchangeable through Einstein's equation, E equals mc squared, right? So when we fuse 2 atoms together, the product on the other end actually weighed a little bit less than your original 2 did. So that differential in mass goes into Einstein's equation, you get a huge amount of energy out. That is the potential of fusion. If you can harness fusion in the laboratory, you can actually get more energy out than you put in our case with the lasers.
And that's exactly what happened. On December 5th, 2022, fusion ignition was achieved for the first time ever by Lawrence Livermore National Laboratory on the National Ignition Facility, or NIF. And I don't think I can really overemphasize what a huge deal this is. Like, scientists and engineers all over the world have been working toward achieving fusion ignition for decades, since the 1950s. See, John Nuckolls was a physicist who spent his whole career at Lawrence Livermore, and he was one of the first to think that ignition was something that could even be done. He and his fellow scientists knew that, theoretically, it was a possibility. They just didn't have a thing powerful enough to be the thing that could squish the fuel together to induce fusion and release that energy.
Then, in 1960, we had the invention of the laser, and John, along with lots of other key scientists here, saw the potential of using the laser to confine the fuel.
Lasers at Livermore started with the Janus laser, sparking a laser legacy of ever-increasing power and energy through the decades, leading up to the National Ignition Facility, which began operations in 2009 as an essential component of the science-based Stockpile Stewardship program. But it's taken that whole journey to actually achieve ignition because making fusion happen is really, really, really hard for several reasons.
So the first one is the laser.
There's 192 beams, and all of them have to arrive at the same time. And each one of those individual laser pulses has to be perfectly shaped to 3% accuracy. And finally, we have to point them at the same point to within 50 microns, or about the width of a human hair.
And the way that laser energy is shaped and amplified as it grows and is directed through the NIF is optics. Essentially, optics are the most advanced and complex glass ever.
NIF is one of the most complicated and expansive optical machines in the world. And it's only through process development and hardening of those optics over the years, through various science and technology advancements, have we been able to drive up the energy to the levels that we have on NIF.
And it's not just the thing we're firing at the target that needs to keep on being refined and improved, but also the targets themselves.
We discovered the big limiter was microscopic imperfections in the capsule, which were then amplified as this implosion proceeded. I want to remind you guys that we start essentially with a basketball and we want to squeeze it down to a pea. So any imperfections in that basketball would prevent us getting down to a pea. This set in process a number of changes. One was improvements in target fab, and then from the design side, how can we find a more robust design?
There's been decades of effort on engineering of how to build these materials and really, micron scale accuracy in building things, which is really impressive when you think about that. I mean, that's smaller than a human hair. It's very impressive.
Now, when your experiments keep getting more complex and the changes you're making are so minute, you need to have a pretty advanced set of tools that can record what's going on in that experiment. And that way you can measure what's changed and improve it for next time. For NIF, those measuring tools are called diagnostics.
We have gone from a suite of about 2 diagnostics back when NIF was commissioned to a very comprehensive suite of 120 diagnostics that has allowed us to see how the target evolves in the few billionths of a second that it takes to actually conduct an experiment.
And when you have all that information to work with about what went into the experiment and then what came out, you need some pretty powerful tools to be able to analyze that data.
The advancements in computing capabilities has enabled us to really do high fidelity simulations and probe some of the degradation mechanisms and develop mitigation strategies and set requirements on targets and understand them better than we've ever been able to do previously.
So with all of this complexity, the lasers, the optics, the targets, the capsules, the diagnostics, the computational analysis of results in the simulations, why do we do it? Why are we so interested in fusion, and in particular in fusion ignition?
So what happened was in 1992, we decided to stop doing nuclear tests. So we have a strategic stockpile that basically is used as sort of a deterrence to prevent massive global conflict.
When Heather says strategic stockpile, she means the United States stockpile of existing nuclear weapons. And when she says deterrent, she means that everyone in the world who has nuclear weapons is basically prevented from using them because they're not the only ones who have them.
The experiments that we do here at the National Ignition Facility and at other facilities within the Department of Energy provide data and provide science tools to help our scientists and engineers continue to maintain the safety, security, and reliability of that nuclear deterrent.
So national security through stockpile stewardship is NIF's most important mission. But understanding how fusion ignition works because of this LLNL milestone also helps us understand our possible path forward for fusion energy. It's really difficult to get across just how much energy is required to make a fusion reaction happen. The fuel inside the target has to be heated to over 3 million degrees Celsius, and it can take over 2 megajoules of energy to produce those conditions.
A megajoule is really, really big. A 2 megajoule laser pulse on NIF is more energy in that moment in time than the amount of energy generated by the entire US power grid over that few billionths of a second.
And even though 2 megajoules is a massive amount of energy to put into an experiment, that fusion ignition milestone in December of 2022 meant that LLNL got out a little over 3 megajoules of energy.
And if you can get a lot more energy out, you can turn that into an energy source, right? Where you could potentially use that energy to keep the lasers running, but if you generate enough energy, you can feed that out to the grid. And fusion is clean. There's no carbon anywhere in the equation, and you only need a very little bit, tiny bits of mass, tiny bits of fuel to make huge amounts of energy. And so that's why fusion is so exciting, and that's why we want to pursue it for the energy mission.
Now, I'm going to keep it level with you. Even though achieving fusion ignition is one of the greatest scientific achievements of our age, it's not exactly like a fusion energy plant is right around the corner.
It's a proof of concept. It's sort of like the Wright brothers' first flight, which by modern standards wasn't so impressive, but that was the proof of concept that launched an entire field of aviation and aeronautics that's developed into what we have today in terms of full-scale commercial travel. That's where we're at right now with our fusion energy efforts, right?
There is a lot of work still to do, and it's not going to be easy. And we're not claiming it's easy. We're also not claiming a particular time that we are promising energy on the grid. I think the point, though, is the benefits, if we can make fusion work, are just enormous. It will be a risk, it will take investment, But as humans, as scientists, it is our job to tackle some of these really fundamental, difficult questions. And we as a national lab, as Livermore, are perfectly placed to take this on. We take on the biggest challenges. They're hard, but they have so much benefit for the nation, so much benefit for the world. I think it is on us to actually push this forward.
If you have more questions for our experts about fusion, fusion ignition energy, or anything else, leave it for us in the comments. Check out these other 2 videos for more on some crazy awesome target science, and thanks so much for watching. We'll see you in the next one.